Welcome to an introduction on the concepts of mechanical advantage, velocity ratio and efficiency for simple machines. So just a quick recap what simple machines are. They're devices which help us do jobs easier. For example, a lever over here, I can have a lever arm to reduce the force, the effort required to lift a heavy load. Sometimes we have the opposite, where we have a bigger load to lift a smaller load, but we lift it for a bigger distance. So some examples of some simple machines: levers, wheels and axles, pulleys, inclined planes, gears and screws. There's a worm, which is a screw. As it rotates, it pushes another gear there. To get some understanding about these concepts, it's very important to understand or recall what work is. So work is a force times a distance. So if I apply a force to something and move it a certain distance, I do work on it. And work is a form of energy. And energy is always obviously conserved. Whether work energy is conserved is a different story, but energy and all up is conserved. If a machine reduces the effort required to do something, then it must be done over a longer distance because of this work equals force times distance relationship. So here's this heavy rock being lifted, and it's being lifted by a smaller force than what it would be if I lifted it directly, but the expense of that is I have to do it over a bigger distance to lift this load, a small distance. So if I want to reduce the force, I have to have a greater distance to do that because of this. The work is the same, force times distance. If there are no losses in energy, that is, if the work that I put into the effort transfers 100% across to the work done to the load, then we can say that the work before equals the work after, or the work from the effort equals the work from the load, or to the load. Just using the definition there of work, force times distance for both of those, and we just rearrange that equation there just to bring the d's on one side and the forces to the other side. I have this little relationship. So this is a relationship coming from work. If there's no energy lost, this is a true statement. Now the reason I've come to this is to introduce these concepts of mechanical advantage and velocity ratio. So mechanical advantage is just the ratio of the forces. So if I apply an effort, and let's say the effort I have is only half as big as the force that is lifted, so this is twice as big as this, I have a mechanical advantage of 2. So that we're going to define the mechanical advantage as this ratio. The force of the load divided by the force of the effort. The bigger the load I can lift with a smaller force, the bigger that mechanical advantage. On the other side, I have the distances, the ratio of the distances. You see how that's opposite. So the distance of the effort over the distance of the load. We may be tempted to define a quantity called distance advantage, where for a given effort distance, then we get a bigger distance moved towards the load. But the reason why we don't put dl over de is because of this equal relationship. So let's define a different quantity called velocity ratio, which is just that ratio, the ratio of the distances. And when there are no losses, just a reminder, because of this relationship here, the velocity ratio is equal to the mechanical advantage. So basically this is the reason why we define velocity ratio in this way, so to make them equal when there's no losses. So here's an example. A man lifts a 3 kilogram object, and let's do some approximations here. Let's just pretend that this is perfectly vertical as a load is over there. That way we don't have to worry about working with components of forces on a slightly different angle. Let's just pretend that straight up. So the question is, find the velocity ratio and the force required by that bicep to pull the arm up. For those interested, this is a third-class lever. So the velocity ratio, the definition of it is the distance moved by the effort. So that arm is going to pull, that muscle is going to pull the arm up some distance, and divided by the distance the load moves up. Now I haven't given you any distances which these things move, so we just need to look at this problem in a bit more detail. And it's not the actual distances which matter, it is the ratio of the distances. Now, if I recognize that these things move in a circular motion, if I take the fulcrum, the pivot point there, which is there at the elbow, I can see a small movement from the effort is resulting in a larger movement for the load, and it doesn't matter how far that moves, the relationship there is pretty clear. So for any given angle that I move through, I could look at this and say, okay, well that traces through one fraction of the circumference of the big circle, and this one goes through the same fraction but of a smaller circle. So just looking at the angle there, 360 degrees in one revolution. If I know the angle I move it in, then I get the fraction of the circumference. So this big circle is the distance that the load moves, and the smaller one is the distance that the effort moves. For the same angle, all this is the same, and I could just substitute this in. So DE equals all that times RE, DL is all that times DL. Taking the division of the two, all that stuff cancels out, leaving me with DE over DL equals the ratio of the radii. So there's my velocity ratio. And just down here, we would have noticed that beforehand, let's put it back, the way the problem was set up, 5 centimeters to another 35 centimeters. Well, the distances of the radii have to come from the pivot point there. So that 35, add that 5 together, 40 centimeters. So velocity ratio, 5 divided by 40, which is 1 over 8, which is equal to 0.125. And assuming that there are no losses, then we remember that the mechanical advantage is equal to the velocity ratio. That is, the mechanical advantage also equals 0.125. Using the definition of mechanical advantage, FL over FE equals 0.125, or 1 over 8. And just putting the summary there. Rearranging this formula to make the effort the subject of the equation, because that's what the question's asking us for. FL over 0.125. FL is just the mass times gravity, the weight force of that load, which is 3 times 9.8. Divided by 0.125, 235.2 newtons. So a larger distance moved at the load, requiring a larger effort at the effort side there. Let's looking at a different example, second example. So here's the box below, simple machine, don't care about the internal workings of it. It just so happens that if I push down with an effort of 80 newtons and it goes through 15 centimeters, well, it'll lift a load of 20 newtons by a bigger distance. Okay, so we have a velocity ratio mechanical advantage less than 1 here. So bigger effort to lift a smaller effort, small distance move to make it move a lot larger. So we want to determine the mechanical advantage and the velocity ratio, and then let's have a look, we'll compare those and see if there's any energy which is lost or not. So for my definitions, velocity ratio, mechanical advantage, velocity ratio straight from the question here, no worries. 15 centimeters going down, 50 centimeters going up, the velocity ratio is equal to 0.3. The mechanical advantage, again from the data in the information in the question there, a 20 Newton load is raised by an 80 Newton effort. So 20 over 80 is 0.25. So 0.3, 0.25, they're not the same. So what does that mean? It means that obviously energy cannot be conserved there, so that they're not the same value. So energy must be lost. Just comparing those, if I look at what the mechanical advantage could be if there was no energy lost, then a quick ratio there, dividing one by the other, 0.833, that's 83.3%. Now I won't do this, but if you go through with the definition of work there, that ratio is going to be exactly the same as the ratio of the work provided, the work done to the load divided by the work that was done at the effort. So this is a ratio, a percentage of the work that is transferred from effort to the load. That is 83.3%, only 83.3% of the effort has gone through to the load. Taking the difference from 100%, that's 16.7% of the energy from the effort has been lost. So we've got some inefficiency in this system. Now let's define this. Let's define this efficiency as being the ratio of the actual mechanical advantage with the velocity ratio. That's the Greek symbol eta, E for efficiency. Doesn't look like an E, but it is for Greek, all Greek letters. Rearranging that, another useful thing there is mechanical advantage is just the efficiency times the velocity ratio. So what would that's the velocity ratio is what the mechanical advantage would be if there's no losses. Well, this inefficiency means it's only a fraction of that. So if the mechanical advantage is equal to the velocity ratio, we have a ratio of 1. Well, that's for a 100% efficient system. Just a little example there. If the mechanical advantage of a velocity ratio is only 0.5, well, it's 50% efficient. Here's another example. The simple machine below is 75% efficient. What effort is required to lift this 60 kilogram load? So 60 centimeters down, only lifting it up 20 centimeters. We have a larger than 1 mechanical advantage, so going over a greater distance to lift a smaller distance. So we're expecting this to be much smaller. The velocity ratio is the distance moved by the effort over the distance moved by the load. So 60 over 20 is going to be 3. Looking at our definition of efficiency and rearranging that, the mechanical advantage is only going to be 75% of that 3. So 0.75 times 3 is 2.25. So there's our velocity ratio, mechanical advantage from these relationships. Using the form of mechanical advantage, the ratio of the load over the effort and forces is equal to this reduced mechanical advantage because of that inefficiency. Rearranging, the effort required is the load divided by that mechanical advantage. The load was 60 kilograms times 9.8, bringing us to an effort required of 261 newtons. If there was no inefficiency, it wouldn't be 75% of that, it would be a third of that. In other words, only requiring less of that force there, but requires more force because it's inefficient. And there are definitions, there are formulas there which we can use, and that's the end of this introductory lesson.